Hello everyone, this is Shravani Madhurakavi, working as Assistant Professor in Aeronautical Department in Institute of Aeronautical Engineering. So today in Aerospace Structures Lab, we are going to know another experiment that is Shear Centre for closed section. So here what we are going to find out is, our aim is to find the shear center of an closed section. So what are the apparatus that are required is unsymmetrical bending structure frame, digital indicator, hanger, mass, and channel section specimen, U section specimen, rectangular section specimen. Okay. So coming to this unsymmetrical bending is nothing but unsymmetrical bending and shear center experiment. It consists of a top plate and a chunk, a bottom plate with two digital indicators, a free end, chunks, and three specimens, that is U, L, and rectangular one. So considering any one of this, we are going to find the closed section. There is also an attachment for finding the shear center of each beam. So this is the experiment that this is the experiment setup where we are going to place our beam in this chunks by loosening the chunks. So the top plate fastens to a top member of a test frame and bottom plate on the bottom member. The specimen beams are secure into the top plate chunks, which indexes around into 22.5 degree steps. So it's nothing but its angular increment will be around 60. The bottom plate has two digital indicators, then can be arranged in 90 degrees to each other for an unsymmetrical bending experiment, or we can do it in a parallel way. We are placing it in the form of a vertical way. Another for the shear center experiment. The bottom chunk secures to the free ends of a specimen and contacts to the two indicators. So here when we see this, these are the two indicators that are deflection indicators to which we are going to add our specimen. So this is the beam setup that we are going to adjust in such a way these deflections can be detected by these indicators. Okay, whenever we are going to add the weights here, the deflections are noted from these displays. Okay, these indicators. So that's what here it is, that the bottom chunk secures to free ends of the specimen and contacts to the two indicators, so that we can read the values by as we add the weights to it, we will get the deflections on the deflection indicators. This arrangement allows measurements of the end deflections of a specimen in two directions. The force is applied to a peg on a bottom chunk. For the shear center experiment, the indicators swing around and the shear beam attached fixes to the bottom chunk. So consider here, this is where we are going to add the weights, and once we add as per the requirement from the left end and to the right end, we are going to get the deflections where the twisting and bending is there, that we are going to take and we are going to do the plotting, and at a particular point where we won't get a twisting, only pure bending takes place, that at that particular point we have got the shear center. So see here, the applied force, look at the figure here, the applied force induces shear stress in the section. So here it induces the shear stress. So when we talk about shearing stress gives rise to shearing force. For equilibrium, the vertical shear force is equal to F. The two horizontal shearing forces are equal here. See, these are the two horizontal. See this, how they are equal to each other. So coming to this, the coupling due to the vertical and horizontal forces are in the same direction, so the section gets twisted. So these are the coupling due to the vertical and horizontal forces are in the same direction, so there will be a twist in the section. So what we need is, we want only a pure bending without any twisting. Okay, at that particular point, till we get it, we are going to do the experiment by changing our weights from the center point to the outwards. Here you get here, beam will always bend when loaded, but unless the load is applied at a position known as shear center, the bending will be accompanied by a twisting action. Okay, so what you see when we consider this U section loaded with a force F, the load set up shearing stress in the section caused by the shear force. That is what we are going to get due to this load setups. Okay. For equilibrium, the vertical forces must balance the applied loads, and two horizontal shear forces must be equal and opposite. The two horizontal forces will form two moments which combine the twist to twist the section. So whenever we are talking here, see, look here, this is the red thing. The rectangular cross section is subjected to the shear force. So this is the rectangular cross section which is subjected to the shear force, and this one is the rectangular cross section subjected to the shear force, that is V2. So, however, if the beam is loaded at its shear center S as shown in the figure, then the two moments cancel out. The beam then bends but does not twist. So, this is a particular point where the beam then bends but not twist. So, there we will get the shear center. Okay. In this experiment, we will purposely load the U section eccentricity. Okay, we'll consider the eccentricity point, and from there we are going to go increase our weights to sidewards, that is left and right. We will shift our position of that eccentricity point, and then we are going to get the values. That is the position at which at each side of the shear center, and measures the twisting action with the indicators each side of the section. So we can then ascertain the position of the shear center, since it is the point of zero twist. That is what, when the two indicators readings are identical, then such point is considered as a shear center point. So look here. So load to the left of the shear center. So here. So the load of the shear center which is to the right. Now when we are going to get two indicators in an identical value, then such load is here. We are going to consider load at a shear center. There will be no twisting of the loads, that the plate, there will be an equal value to both the sides of the indicators. At that particular point, we are going to get the shear center. Okay. So coming to the procedure. Before getting into the experiment, let's know what is shear center. Shear center is nothing but where we will find a point where pure bending will take place. Okay, and there will be no twisting. So that is what we are going to measure during this experiment. Okay, for this we want apparatus like that. Apparatus are unsymmetrical bending unit and structural frame. This is called unsymmetrical bending structural unit, and also we have digital indicators for determining the deflections over here, and we have a closed section B. This is the setup that we are going to fix. This is how we will loosen and we will change this, and this experiment is also conducted in other way, that is using a open section. So here we have fixed a closed section B. For this we are going to find out the pure bending, that is shear center for it. So let's start. So here we have a hanger. Here we have measured and we have set our beam in such a way that it should be pointed in the center. So here we are going to add a hanger, to which we are going to add the weight hangers to it. We will take around 300 grams, that is This each weight is of 10 grams. Okay. So we have considered 300 grams over here and we have set it. Now set these two dial gauge indicators which are used for measuring deflection, right? We are going to set it to the origin first. Then set these two for the origin and then when we set this to the origin, it is nothing but it is in a pure bending position. That shear center is applied over here. Now when we are moving our hanger from this side to this side, that is nothing but from this origin to some points. That is each point is measured as 5 mm. So when we go positive 5 mm and when we come negative 5 mm, where we are going to get the pure bending, that is what we are going to calculate. So see here, and whenever we are moving here, there will be some deflections over here that we are going to measure and we are going to tabulate it. So for tabulating it, we are going to take eccentricity of load, take in the tabular form as eccentricity of load, and then left hand reading indicator and right hand reading indicator. This is going to be our right hand reading indicator and this is going to be left hand reading indicator. So change our position of this and wait for the deflection over here. So if at all it moves, if it gets deflected towards right, we are going to write it in the right side hand deflection. And then that is nothing but there is some twisting with bending. So we are going to reach to one point there, a pure bending takes place where the shear center point is reached. So as I said, we are going to note down the right hand side reading and left hand side reading and eccentricity load. What is that we are giving over here? So by that we are going to plot a graph and then we are going to get a required plot where the particular point is noted down and that is nothing but a shear center for a closed section. Okay. So this is the values that we are going to get from the left indicator and also the right indicator and how the eccentricity of load is given. So here we will start from 0 and then we will take these values and also we will shift our loads to this value and each point is considered as 5. So these are the values that we are going to get when we do the experiment. So finally, we are going to take the left hand side readings and right hand side readings and we are going to plot and that particular point where it makes that is considered as a shear center. Okay. So what are the precautions that we need to take is ensure 0 reading on the dial gauges before loading the beam. Note down the readings with the parallax error. Do not disturb the apertures during the experiment. Finally, what is the result is for the shear center for the rectangular or a closed section is at the center of gravity. Particularly from the graph, the dial gauges reading coincide on the y-axis. That is, the shear center is at the center of gravity of a rectangular section. So this is what we have obtained. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.